Hi everyone. One of the things that we're talking about this week is looking more closely at absolute value functions, and then we'll actually go a little bit further and talk about solving equations and inequalities with them, and then we'll get into some applications and why we might care about using these. So just as a reminder, here is the function y equals the absolute value of x. Again, it's this V-shaped graph, straight line segments with a sharp corner at the vertex here at the origin. It's domain and range right there. One thing I wanted to point out, because we've just been talking about inverse functions, is that while this is a function because it passes a horizontal, or sorry, because it passes a vertical line test, this is not one-to-one because it does not pass a horizontal line test. Just about anywhere inside the range of the function that I draw a horizontal line, we hit the graph twice, which again means it's not one-to-one, and so it doesn't have an inverse. Can make a note about that. It's not one-to-one. Being one-to-one, again, basically means that if I ask, hey, when does a certain y value come up, you give a single answer in response. If you look at what's happening here, when I ask if a certain y value comes up, probably it happens twice. So what this does then is affect how we solve equations and how we work with absolute value functions. So for example, say I wanted to solve this equation, finding value, the value or value of x, that when we take the absolute value gives us 1. So maybe take a second, pause the video, think about that. Okay, welcome back. So if I'm just thinking about numbers whose absolute value is 1, certainly one option would be that I could take the absolute value of 1 and I get 1, and so x equals 1 is a solution. But on the other hand, the absolute value of -1 is also 1, and so x equals -1 is also a solution. So the solutions here to this equation are both 1 and -1. Those both solve the equation. If we want to think about that graphically, asking where the absolute value is equal to 1 means treating this as a y value and looking for the x that it goes with. So if I look at y equals 1, there it is. I'm looking for points on the graph that correspond to that. Here's one, here's another one, at x equals 1 and x equals -1. So we see that there are two places that happen, that value comes up at 1 and -1. Those are the two and only two solutions to that equation then. Okay, well, something like this second example, where is the absolute value of x minus 2 equal to 1, I can treat in pretty much the same way. Forget about this for a second. The absolute value of something is equal to 1. Well, think about kinds of things that this could be, right? Again, not worrying about the fact that it's x minus 2, it's just something. What kinds of things do I take the absolute value of and get 1? Well, I just saw that 1 or -1 are the two, and again, only two values or numbers whose absolute value is equal to 1. If you want to think about what's going on with this x minus 2, it's a shift to the right. So what I can do is say, okay, well, x minus 2 could be 1, or x minus 2 could be -1. Okay, well, if x minus 2 is 1, then x itself would have to be 3. And if x minus 2 is -1, x itself would have to be +1. So again, there are two possible solutions. X could either be 3 or 1. If you think about taking this absolute value function and shifting it over to the right 2, it would look something like that. And then graphically, what we're asking is where does it pass through 1? And hopefully you can see right there when x is 1, and right here when x is 3 would be the 2 places that that happens. We can adapt this idea then to solve things that are more complicated where, maybe I either can't or don't want to think about it as shifting. Do one more example real quick. Let's say we had equal to 9. So we could, if we wanted, dig into this and pick out all the transformations. These are things that we can describe. And then we could think through, okay, when would that intersect 9 then? So I could use some kind of a graphical argument like that. Or I can use the algebra skills that I've just sort of developed. I've kind of got my head around how this absolute value thing works now. But to do that, I should start by getting the absolute value term by itself. The stuff around the absolute value on the outside, it's easy enough to move that around and move it to the other side of the equation. And when we do that, we end up with a thing that's going to be easier or more straightforward anyway to interpret. That's going to work kind of more in line with what we've just been talking about. So really what this thing that we started with, 2 absolute value x minus 3 plus 5 equals 9, an equivalent way of looking at that equation is figuring out where the absolute value of x minus 3 is equal to 2. I have run myself out of room, so we'll go right here. Now again, without worrying about that just yet, just looking at the fact that we're talking about an absolute value being equal to 2, think for a second. Again, this would be a great place to pause the video and try this for a second for yourself. Think about where the absolute value of something would be equal to 2. So on a number line, that would be either positive 2 or negative 2. So what we have then is that x minus 3 could be positive 2, or x minus 3 could be negative 2. If x minus 3 is 2, then x itself is 5, adding 3 to both sides. And if x minus 3 is negative 2, then x itself is 1. And those are our 2 solutions to this equation then. Okay, so that's kind of the basics of how the absolute value thing works. We'll do more examples and practice problems and everything in class, and kind of see, what else can happen. We'll also get into solving inequalities and talk a little more about how we can approach that. But this should give us a good starting point for dealing with absolute value equations. The other thing I wanted to mention real quick are piecewise defined functions. These are just functions whose rule operation, like the way that they turn x into y, depends on what x is. So a good example for just kind of thinking about it might be something like really anything where the way the rule applies depends on something about where you are. So it could be something that's maybe age dependent, like you can't rent a car unless you're at least 25, maybe. I don't know. Once you're older than that, it kind of doesn't matter as much anymore. I think it's 25, whatever. That's a rule, like, hey, you want to rent a car? Okay, it works like this, and you pay this much money, and you sign your name and whatever, if you're over 25. But if you're under 25, then you just can't do it. Tax brackets would be another example. I know it's a really exciting one, but if your income is, above a certain amount, then you pay this much. If your income is between certain amounts, you pay this much. If your income is below a certain amount, you pay that much. Tax brackets. Anything like that where to be able to tell you how a thing works, I have to know a little more information about your situation first. That's what a piecewise function really does. The way we write them is something like this. It's still a function, so we still, call it, something, f in this case. It still has a variable. It's equal to. This big curly brace just means these two pieces go together. And then the first part is the usual function representation, symbolic form, formula kind of thing. And then this part tells us when we use each piece. So really all this function says is that if the value you're plugging in is less than 0, so if it's negative, then you use this rule, and what you do with your x value that you're plugging in is you add 2 and you ignore this altogether, because if the x value fits into the first piece, right, if it's less than 0, then that's the piece of the function that you use, right? Much like, I don't really care how the tax bracket works for someone who makes, $10 million a year, because I don't make $10 million a year. So it doesn't apply to me, right? So I follow the rule that applies to me. It's the same idea here. On the other hand, if x is bigger than or equal to 0, we use this piece and we ignore the other one. All we're really going to need to be able to do with these is kind of interpret what they tell us. So, for example, if I want to find f of -3, I take, okay, there we go. I take my x value -3, and I look right here, and I decide which one applies. Okay, if x is -3, -3 is smaller than 0, so I use this, and I plug in, and I get -3 plus 2, which is -1. And that's it. I don't use the other piece of the function at all, because the value that I started with, -3, doesn't fit into this. So I just sort of ignore that that's even there, and just evaluate using the first line, the first piece. Okay, so again, good place to pause and try these other three real quick. -1 fits in here, so I plug into this. 0 fits in right here. 0 is greater than or equal to 0, so ignore that, use this, plug in 0, get -1, and then 2. 2 is bigger than 0, so ignore the first line, use the second line, and plug in 2. To get 3. Okay, that's how you evaluate a piecewise function. We'll talk a little bit in class more about graphing and just a few more examples of this, but that's the basic idea. For both of these things, I've got example videos up as well if you want to take a look at those. Otherwise, I hope that helps and makes sense and gives us a starting point for what we're going to do together in class. And I will see you all in class.